HSN delivers PNT services through a mesh of inter-node communications. In this demonstration, we're going to show a node switching its time source with minimal interruption to timing stability when this original source node is disabled. To propagate global time throughout HSN, at least one node is required to have a connection to a global time source such as a GPS-disciplined clock or oscillator, also called a GPSDO. When a node determines that it has a valid time input, currently via a pulse per second input signal with its accompanying NMEA timestamp message over a serial link, it self-designates as a timing grandmaster or GM node and advertises its status so that other nodes can synchronize with it through the exchange of round-trip time measurement or RTTM packets. These packets are modulated like Wi-Fi, but with a bandwidth of 15 MHz for most of the packet. A wider section of up to 40 MHz may be used for the synchronization sequence. In this example of an HSN network with two GM nodes, the others will synchronize with their neighbors to get the best connection to one of these two, leading to a node hierarchy given by these colors: green for one wireless hop from a GM node, yellow 2 hops, orange 3 hops, and red 4. If the upper GM node is disabled, its descendants will now select nodes descended from the remaining GM for their own time sources, which increases the number of levels in the network hierarchy to 4 hops in this example. More hops increase jitter in the time, approximately by 1 nanosecond per hop, but crucially a link to global time is maintained, allowing for the disabled GM node to be replaced or repaired without network failure. For ease of analysis, we're going to show a simplified network in this demonstration of 3 nodes with 2 GMs. The GMs are numbered 2 and 3, and the 1 hop descendant is node 4. The test setup uses a GPSDO for PPS, which is split 3 ways, to nodes 2 and 3 so that they can self-designate as GM nodes, and to an oscilloscope which is used to show the time stability of all nodes by comparing each of their PPS outputs with that from the time source. Nodes 2 and 3 also have a serial link over which they receive the NMEA timestamps associated with the PPS input. These serial messages originate from a separate time source, in this case, a U-Blocks evaluation kit, which is also a GPSDO. In this demonstration, the nodes communicate and exchange RTTM packets using a single carrier frequency in the 5 GHz band, over a wired connection to keep the equipment close together and make the display of PPS outputs on the oscilloscope straightforward. Here we have the 3 nodes that we'll be using for the demonstration that are connected at RF via coax cables and the splitter in the middle. The U-Blocks module at the bottom is providing the NMEA timestamps, and the PPS splitter is dividing the PPS output from our time source between nodes 2, 3 and the oscilloscope, whose output is going to be mirrored on a screen to make it a little bit easier to see what's going on. There's the time source and the antenna cable to the GPS antenna stretching upwards to the ceiling and the roof. So here we have the HSN GUI, and the data being displayed is coming over a serial link from node 4. You can see the RTTM trace of node 4 in the middle, that red squiggly line at the top, and the sync hierarchy shown on the right hand side there. So nodes 2 and 3 are self-designated GM nodes. They have PPS and NMEA inputs, and so are able to provide time to other nodes via RTTM exchanges. We have node 4 that is deriving its time through RTTM exchanges with node 3, and node 2 currently does not have a descendant node. The traces on the oscilloscope above are using the similar colors, so node 2 is green, node 3 in blue purple, and node 4 is red. And in yellow we have the PPS input from the time source. So just to explain the values in the time offset column, the GM nodes are synchronizing directly with their PPS inputs, and the values that we see there, either plus or minus 4 roughly nanoseconds, is due to the sampling frequency that is used to sample that 1-bit signal. Whereas node 4 is reporting a wider range of time offset values that are derived from the RTTM exchanges. And so what we're going to show in this demonstration is node 4 switching its time source between nodes 2 and 3 as nodes 2 and 3 are powered off. We'll see that the PPS output from node 4 stays well aligned with the input, the yellow trace. So to begin with, node 4 started off being attached to node 3. Node 3 has just been powered off. We see node 4 very quickly changing its grandmaster to node 2. Node 3 will be powered back on, so its blue PPS trace will reappear shortly as it synchronizes once again with its input time source. So to begin with, it's going to synchronize with node 2, as node 2 is transmitting RTTM packets indicating it's a time source, and node 3 has not yet heard enough enemy timestamps for it to self-designate as a GM node, but after some time it will adopt that state. We're just going to speed up some of these sections to show the nodes returning to synchronization after having been turned off. And there we go, node 3 is a GM node. And now we're going to disable node 2, now that node 3 is as well synchronized. And so the green trace will disappear and node 4 will switch to node 3 as its time source. See the trace of node 2 moving across the screen there as it returns to being synchronized with the time input. And once it's done so for some time, it's going to, as node 3 just did, going to return to GM state. HSN can maintain synchronization through the mesh of RTTM exchanges even when some nodes are disabled. Our next hardware revision will include support for the Precision Time Protocol over Ethernet as an alternative global time source to PPS plus NMEA. We are also working to improve network sync resiliency through the holdover capabilities of the high-quality oscillators in our hardware, so that nodes run in holdover mode and maintain communication for a time, even in the absence of any GM nodes.